night, you should see it no later than, let's say, 9:30. I don't have to do any editing to these. I'm going to keep them raw. Any mistakes I make, that's on me. Any funny jokes that you make, at least it's not your full names. I think can come back to haunt you in the land of the internet. So there's that. Uh, if you have anything that you want not recorded, let me know. I will gladly pause the recording for you before I post it, or I'll edit it out of the recording, or just hit me a private message in Canvas and we can talk one-on-one. As always, I am available to you guys whenever you need. Let me pull up the
Hey,
agenda.
Justin,
Yes, what's up, Eric?
got a question for you about the message I sent you in Canvas. Were you able to go over that or not?
Are you, whoops, excuse me, I'm on the wrong screen. Is this about the employment opportunity?
Yeah, yeah. I
Yeah,
sent you like a little bit of information and then an attachment that you could look at. It's my resume. That's all it is.
I
If
did.
that helps.
Good. Yeah, it does. And actually, let's see. I got one other question. Dustin and I were talking about that, so I'm gonna address that. Let's move that at the top.
Okay.
Okay. Oh, my doppelganger's here. Carlos is here. I'm just gonna start calling him Twin. What's up, Twin? How you doing? Okay, so about the employment opportunities, let's refresh. It's my don't apologize at all, Carlos. You're great. One of the things that I'd like to do, aside getting you excited, enthusiastic about the field of electronics and computers, is also help you be viable and get connected with employment in field of computers and electronics. So I have three, potentially four, but I'm gonna go with three employers that are currently I'm in talks with about having people come uh, work for them. They're trying to we're trying to negotiate how many people they're willing to take on who might not necessarily have experience, but we're going to be hard workers. I can tell you right now, one of them is an electronics shop, but they're looking for an assemblyman or two. Assembly person, excuse me. We're not gender specific. Another one is a metal craft like CNC shop, but they're actually looking for somebody to do specifically computer support. I'm trying to find out what their specifications are because they have a unique hybrid system where part of their system's managed remotely, but they need somebody on premises, and I'm trying to figure out exactly what they want. And if it's more than one person, there's a third person. It's in biopharmaceutical um, forum, that area, and they're looking for somebody to do small assembly work with electronics and light soldering and automation processes. So those are what I'm looking at, and there's a fourth one that I'm talking about, but in all honesty, this employer seems a bit flaky, so I'm not going to put my eggs in that basket. I would like to make sure that I can gather all of the information first before I can present it to you as students so that you know whom you could potentially be working for, and I'd like to make the best fit possible so that it's a lasting relationship. I don't want you to come back 3 weeks later and be like, dude, that was bunk. I didn't like it at all. I want you to maintain your enthusiasm for the field as best as possible to make that connection that fit. So I'm sorry if I didn't get back to you. My intent was to bring this forward to you guys in the meeting. It looks like I won't have definitive information until next week. Really quickly, any questions about that?
Questions. Are they all one question. Are they local to SCV or no?
They are actually all local Santa Clara. For those of you, like I know Pam, you're up north, AV area, right? So these are all in SCV. One of them's in the industrial, and I don't want to give the names of these employers currently because we're recording, but I will let you know off recording next week when I have all the information to give to you, and then we'll talk about it. Good
Sure,
seg.
sounds good.
Great. Good, excellent. Good segue. One of the things that I'd like to do, and I might not make this a point basis, but this might be something that some of you might want to get into, is we don't have enough time to go into resume stuff for employability, but something I really want to push forward because I think it's super important. I think it's lacking in the areas of technology are people who can put together really good cover letters and cover pages for their resumes. So I am willing to spend some time, even if they're not graded assignments, to put together something so that you can come out of this class at least with something that gives you a modicum of employability, something more so than you'd have before. Unfortunately, I feel like it's something that we as instructors fail to do because we feel like it's out of our expertise. I do a lot of hiring on a consulting basis for other areas, so I feel like I'm kind of uniquely experienced in this, and I would be happy to help you guys as students in order to put that together. So that's something I might be considering. We'll just consider this for after midterm for something that we can throw together, and it would be kind of a as needed basis, not graded, just an additional value added for this class. So if you guys are interested in that, you can go ahead and send me a message ahead of time so I know exactly how much I should be thinking about this. Excellent. I see a thumbs up. Cool, Eric. Excellent. Good to know. I just think it's something that we typically don't have for members of our field. So I'd like to put it together. Also, professional organizations. Nobody ever talks about joining a professional organization for us, not necessarily a union, so to speak. But I think it's important if you're going to be in the field, especially long term, to connect with a professional organization. Usually, like the cost to join a professional organization is something on the order of like $20 a year, but it can mean huge dividends for you once you get connected and you have certifications, or you're pointing towards certifications, and you have the networking aspect. So that's something else I wanted to point out. Any questions so far on employability or cover letters or professional organizations? Cool. Moving right along. Okay, next week. Next week, I'm going to open up the midterm. I'm going to do something very unique because I feel like it's all fundamental stuff within the midterm that we started talking about since week 1, but we'll continue to build on this now that we're moving into AC, alternating current. If you happen to have a revelation within the realm of alternating current that better allows you to understand the foundational content, then all the greater. So I'm going to open up the midterm. I'm going to leave it open until, I'm going to say, the end of the term. And I will leave it to you to do the midterm before the end of the course. It is a large point value. I hope that you do it. I will try my best to give you a reminder before Thanksgiving, like, hey, you haven't did your midterm if you have not yet done it. But I feel like at this point, when we start to talk about alternating current and we start to bring new components into the curriculum, people start to have these, aha, I totally get that now. And it makes their lives easier from then on, but it doesn't do them justice when they've already taken a midterm and they haven't quite grasped the content. If you guys are with that, give me a thumbs up. If you want me to give you only, because if you're a habitual procrastinator and you only have, you want like a time limit, let me know. I will lock your midterm for you. You let me know, guys. Thoughts, feelings, concerns?
Cool with me.
All right, excellent. I got thumbs up all around. I will make an announcement before Thanksgiving. After Thanksgiving, I can't make any guarantees. I'll let you know before the end of the term. You'll see it. You'll see it on the Canvas shell. Okay. So that being said, I want to put the entirety of next week into midterm prep and going over fundamentals that we're going to talk about some of the stuff this week, and then also kind of melding that with stuff that's pertinent to the midterm but also moves into the AC. We're going to be talking about inductance next week. So I think it all starts to come together. Inductance, I think, is kind of difficult to look at if you don't have the fundamentals, but once you start to see how they work together, it just makes more sense. And I hope you guys feel that way too. I don't want to penalize you for not having the fundamentals just because it's difficult to grasp. So that I understand. Let's see. I opened up a new virtual lab this week. That one's going to be available. I'm actually going to be opening up a second one. And that one will be only 10 points. The first one is 25 points. And that one's based around capacitors. Capacitors, I think, are a fundamental component within electronics. Oh, geez, my internet connectivity is stable. Guys, give me a thumbs up if you can still see me. Did I drop off the face of the planet? Okay, cool. I'm here. I just got a little notice that my internet was becoming unstable. Um, I'm in a grad program. Thank you. I appreciate the thumbs up. I know you guys are listening. I love it. I'm in a grad program with guys and gals who are literally doing their master's work and they don't know what a capacitor is or what a capacitor is for. Somebody in my position for them has failed. So this is a perfect time because we're moving over into AC. I want to talk about capacitors, and we are going to make that our first stop in this part of the lecture. We're going to move into the first half of AC fundamentals. I split it up into 2 lectures. First half will be tonight if we finish it. If not, I'll move it over and I'll record it and put it online. And then the second half will be next week because that'll help us talk about another component, transformers, and it'll talk about inductance. That's what it was. Great. Anybody have any questions before we jump into this? Groovy. One other last quick notice. Apparently, I'm getting evaluated by the department chair. So he may, you probably guys know Lee Hilliard. You might have taken a class with him. He might hop in and just be part of the lecture and just listen in. So that's cool. Make me look good, guys. Or kind of mess with him. You can mess with him too. That's a good idea. All right. Let's get going. Can you guys? No, you cannot see my screen yet. Now I can't see my screen. Can you see my screen?
Yes.
Excellent.
Yes.
Let's kick it off. All right,
We're good. Yep.
great. We're going to talk about capacitors. I'm not going to say that I'm criticizing the text, but I feel like maybe it was a little lighter than it should have been, and I want to get a little bit deeper, at least have some more conversation about what capacitors are, but also, more importantly, I want to give you the opportunity to ask questions and talk about exactly what, why, how, and where we use capacitors. Typically, if we were in person, we'd be able to plug them in and play with them and measure them, but we can't do that here. So we're in the virtual lab. I want to give as much opportunity to talk about basic components as possible. First point is we have to make a warning. Capacitors store energy by nature. We'll get into the details later on. If you touch a capacitor without it being discharged and you touch both leads, you could get shocked. Depending on the size of the capacitor, that could be wet your pants or a trip to the hospital. So let's get that out of the way. Please do not touch a capacitor without discharging one or knowing that it's discharged. And we will have another demonstration on capacitance discharge after this. All right. Here we go. And nothing's working. Okay, excellent. Can you guys see my screen now? It flashed. Somebody can see my screen?
I can see it. It
Okay.
shows capacitors. What are they?
Excellent. Fantastic. All right, let's knock this out. Okay, so capacitors. Capacitors, what are they? Excellent. That's great. you're practically halfway there. Um, the best way I can describe a capacitor in lay terms, so it's just something I had to do with somebody who was in a master's program last night, is they are like batteries but are not batteries. Essentially, not essentially, their job is to store energy, but their methodology for handling energy are different and their applications are vastly different. Batteries, for one, let's pull this up. Batteries, for one, create energy, typically through chemical reaction, and that chemical reaction is converted to electrical energy, and it's then forced out of a terminal and then is used in a system or a circuit. That is how a battery is used. Capacitors are different. Capacitors do not create energy via reaction. They don't produce electrons. And I think it's very important to know, and I thought that was a very fundamental proposition when we're talking about capacitors, but there are people who should be much smarter than that that don't understand that, so let's get that out of the way. It might be on the test. Capacitors do not create energy. They don't produce electrons. What they do is they store energy within fields inside of their physical package. They are able to take electricity, or excuse me, energy, and store them in fields. And we're not going to get into the details of field theory, but you're going to understand a little bit more of that by the end of this lecture, I promise. And it's also worth noting that they are in almost every electrical device. Every electrical device, because they have so many amazing practical uses. Let's see. If we can sum things up very briefly for a capacitor as far as their performance goes. Capacitors, their ability to store is much smaller than a battery. Much, much smaller, that you would get price per pound. But their discharge and charge rates are exponentially faster, resoundingly faster than a battery. Batteries are great for long-term mass storage. Batteries cannot discharge enough electricity in order to create the kind of forces or outcomes that we need in our systems. And I'm going to try and describe that to you. Any questions so far on just the base concept of what a capacitor is? If you can see, this little guy in the top right corner is a capacitor. Oh man, where'd my screen go crazy? Let's do that. And the symbol for a capacitor looks like this. It looks like two T's turned over with their tops towards each other. There's another symbol that you may see if it has an arrow through it. Any symbol with an arrow through it means a variable of some of that that component. So it's a variable capacitor. The capacitance can change. Also, there's one with a curved side, and that means it's polarized. It means it's intended to be used in one direction based on the application. I'm not going to get into that until much later. Let's say 2-3 weeks from now. We'll talk closer to Thanksgiving. If you have any questions, please let me know. All right, then I'm going to ask you a question. Okay, I need to store a large amount of energy. What would I use? Pam, would I use a battery or would I use a capacitor?
Uh, shoot. I'm gonna say capacitor.
If I'm storing
Oh,
electricity for a large amount of time,
oh wait, battery, battery. My bad, my
that's a
bad.
good choice. I know, we just, it's all good. Exactly. If you're looking for long-term storage, a battery is your choice. Capacitors are meant for, well, we'll get into that in a second. I don't want to give away all the secrets right now. All right.
Hey, Justin, I'm sorry to cut in. I missed some real quick due to distractions on my end. Would you say the symbol with the curved one side was?
Uh, so for
Polarity.
polarity, capacitors with
Ah,
polarity.
okay. In all of our prints, that's the only one I've ever seen is with the curved side.
Now, correct me if I'm wrong. Is the curved part the positive and the straight part the negative in the polarity, like the diagram
Yeah, so the curved
symbol?
part is the anode. So yeah.
Okay, yeah.
Oh, you know what, Harley? You work in all AC though, right?
Um, not entirely, but for our purposes, yes.
Okay. I think for the general hobbyist with small capacitors, you're going to see a typical nonpolar capacitor.
Right. Okay. I have pictures of the ones we work with. They're like gigantic structures. They're like not
Do
little.
they do the polarized capacitors have like a white stripe where the positive on the side would be, and then the rest would be like a solid color?
The stripe is typically the negative side.
Oh, okay, I had it backwards then.
Yeah.
Good to know.
Yep. Dude, and Harley, I would actually love to see pictures of those, and if they're cool with you to put them in the future lectures, that would be awesome.
I think they're considered sensitive, but I got a bunch of pictures of out of service equipment that may be, it could be in Australia for all anyone knows. So
Okay. Good stuff. All right. That's why I ask. I appreciate it.
I
Well,
can talk about that later more a little bit.
good deal. All right. Excellent. Well, talking about size, measuring capacitance is kind of a big deal in the game. A capacitor's storage potential is called capacitance, and it's measured in a unit called the farad, named after Michael Faraday, excuse me. This guy is a straight Mac. Um, Besides the fact that he looks like the creepiest dude on the planet and you would not want to run into him in a dark alley, I think that's everybody at the time. Michael Faraday, what are some of his claims to fame? Well, for one, he grew up in a town called Newtington Butts, and I thought that was pretty notable. I don't know why or how I remember that, but I've always remembered that about him. He, aside from being a great physicist and chemist, he actually has a civil law degree from Oxford. He discovered practical applications for chlorine, new renditions of carbon. Actually, I got some notes on him. I got a ton of notes on this guy. He is a phenomenal study if you get a chance. He liquefied gases for the first time. He basically created the original Bunsen burner. He discovered benzene, discovered the laws of electrolysis, or at least one of the four laws of electrolysis. He was the first reported observer of the effects of quantum size, which a person who was living, I think he was born in 1730, I'm gonna get fact check on this, early 1700s, mid 1700s, was able to see the effects of nanoparticles and quantum particles is mind-blowingly huge. He's responsible for today's field theory, diamagnetism. We can go off on a tangent forever about how cool this guy was. Creepy as all get out, but the dude was a straight genius. And because of his great experimentation, we name the measurement of capacitance, the farad, after him, after his last name, Faraday. Just so you know, a farad is an extremely large amount. So we typically talk about microfarads when we're looking in working with hobbyist equipment or small electronics applications. A farad capacitor can store 1 coulomb. So if you guys remember, a coulomb is 6.25 to the 18th power. So that's like 6.25 billion electrons. Far more drops of water in the or far more electrons in that space than there are drops of water in the ocean, just to give you some perspective. So a farad capacitor can store 1 coulomb of charge at 1 volt. So it's the same as saying, I can turn this around. A farad capacitor can hold 1 amp second. So 1 coulomb's worth of electrons at 1 volts pressure. I don't know how to describe how hugely large the number of electrons are in a farad. So typically, unless you're in Harley's field of work, you're not going to be messing around with anything close to that. Um, to hold a farad of capacitance, we would need a 2-liter bottle. So that's why these little guys, I don't know if you can see my mouse right here, these little guys are the scale that we operate on, typically microfarads. Harley, off the top of your head, if it's sensitive information, don't feel you have to disclose, but what's the capacitance rating with some of the equipment that you work with?
So like the set that I was just working on last week, they're these huge racks of. They're usually like 14 sets of 14 parallel capacitors in a set of 14 series arrays.
Okay.
And each one is going to be like, I think they're roughly about 1.5 microfarads at 24,000 volts.
That's still a huge number.
Each individual one. I mean, and then you have 14 arrays of in series of 14 in parallel.
Gosh, okay.
I don't know how to explain it better than I'm explaining it, but
So for the rest of us that work, our minds work on like the scale of things that we can organize and see, the number of electrons that holds is phenomenally large for that unit of measure, the farad. That's why when we're playing around with capacitors, we are looking at billionth of a billionth scale on of a farad. We're looking at the microfarad. So when we're playing around in the, thank you for that, Harley. By the way, I appreciate you sharing that. When we're playing around in our virtual lab in our simulator here, almost everything is going to have a U to prefix the number, or to postfix the number, because we're talking about 1 microfarad or 300 microfarads, very small number comparison to the unit number. All right. Okay, so
I don't want to steal your thunder, but real quick, I can share my video, and I have a picture on my phone that I can show, and it's gonna not be the best example, but I can show
Please,
you what one of those arrays.
please do.
I don't know. Can you see my screen right now? Because I can't see my screen right now.
Go ahead. You
Hold
should be able to share right now.
on. My video is frozen. Can you see that? Because it's showing me that I'm frozen.
No, I can't see anything, bud. Oh, there you
Okay,
are.
right.
Oh, there it goes.
So that's one rack. On either side, they're depending how they're configured, they're in either series or parallel. So there's 4 tiers. There's 14 on each side, and certain sets, depending which set of harmonics they're filtering or what they're correcting for, will either be in series or parallel. And then those racks will be in series and parallel, and the frame is acting as a connecting electrode between sides. So the case is considered energized on those.
Wow. All right. That is a lot of
They're
electricity
pretty
to be playing
intense
around
pieces
with.
of equipment. Here's another set that's hung. That's for 500,000 volt DC for harmonics filtering.
Jeez.
Let me see if it's it.
Oh wow, look at
I don't know
that.
if you can see those arrays, but they're huge racks. It's the scale of things that we work with is so macro, it's ridiculous. It hurts my head.
I can't imagine. So we're gonna get to it in a second, but Harley, I got a question for you. If you don't mind sharing, do you know what kind of dielectric material is inside? It's probably not ceramic, right? I would say Teflon
I
maybe.
do. I do know what's in it because one blew up on me like 2 weeks ago, and the smell's still in all my work clothes. They're non-PCB mineral oil, inhibited mineral oil.
Oh, okay, that's
Each
interesting.
one is about a gallon and a half, and someone broke one open and it like sprayed me down, and it's a horrible smelling stuff.
Okay, all right, mineral oil. That's so wow. That's
Most
gnarly.
of the high voltage equipment you're ever going to encounter is mineral oil. Some of the bigger stuff's SF6, and then some of the smaller stuff is vacuum insulated.
Okay, vacuum insulated. That's good to know. So we're gonna talk about exactly that right now. Let me share my screen again.
Is that why your girlfriend's mad? 'Cause you smell like mineral oil? No, I'm just kidding.
She was not happy when I came home reeking like mineral oil with a pile of things that I needed her to wash for me right away because she got a new dryer that has like I don't even understand how to use it. It has like 47 different wash modes and dry modes.
Oh man, first world problems, guys. It's rough.
Yeah.
All right.
There's like clean and it's crazy.
So let's look at back to capacitors and away from Harley's mineral oil escapades. It caused his girlfriend to be angered. We were not even going to touch that one. We're not going to touch that one. Anyway, so capacitors have two terminals, just like a battery. Excuse me. And they're polarized, so one side's negative, one side's positive. And we're not looking at macro applications. We're going to be looking at very micro, we'll say hobbyist or small electronics applications here. And these terminals actually are connected to conductive plates. And these conductive plates, you can see here, or maybe you can't, are these yellowish orange on either side, and they are separated by an insulator. So like for these industrial applications, mineral oil is one of the insulators that they use. They're always going to be a dielectric material. A dielectric material could be something like mica, Teflon, ceramic, glass, even air. I know for some of the NASA applications for stuff that they use to wake up some of the rovers, they use a a filtered mica glass combination as their insulator, which is really unique and also extremely difficult to make. Um, and also, I want to point this out. When we're talking about dielectric materials are materials that will polarize when they're exposed to an electric field. So they will have essentially a sense that knows which side is positive, what side's negative, and they will push things away from who's outside my house, from those poles, which is kind of like the bias in the original voltaic pile when we were starting to talk about batteries, I don't know, at the beginning of the course. So when a charge goes through these guys, what's happening is the plates never touch, right? But they allow opposing charges to be held within this electric field, and it pushes them away. And what's happening, we call voltage potential difference, right? We start to create a potential difference within this component, within this device. It's this potential difference that is built into a field, not within a chemical construct like a battery, that allows capacitors to charge very quickly and discharge much faster than a battery ever could. There are some case edge scenarios that I'm thinking of, but we'll talk about those another time. Any questions? This is a lot to throw at you. I totally get it. It's going to make a lot more sense in a second, I think. And I hope that the lab, I reconstructed the lab this week on the premise of around capacitors so that you can see them in action in a meaningful way. Okay, so capacitors must be charged, right? We already discussed that they do not produce electricity. They don't create electrons. The electrons are going to flow from the battery to the capacitor. Electrons gained on one plate are released from another plate. Or excuse me, electrons, equal numbers of electrons that are gained on one plate are released. There's no creation. There's no chemical reaction that creates electrons. Any questions right now? Everybody's strangely silent. I wish I could see your faces right now, because this is the part where people's faces are like, huh? Eric's thumbs up. All right. The charge carriers, I was saying electrons, but you can think of the inverse too, positive charge carriers or the lack of electrons. When charge carriers inside become highly polarized, that means there's clearly a positive side, there's clearly a negative side, and they're pushed apart from each other. That's when the voltage appears, because we're seeing a difference. It's a potential difference between one side of the capacitor and the other. When this happens, when they've reached a critical state of capacitance, which happens to be the voltage of the power source, the electron flow, for lack of better terminology, stops. I don't want to ruin it for you. I was going to talk about exponential buildup and then exponential shed, but you're going to see if you do the we'll kick into some of the lab tonight. I think you'll see, you can actually see the electrons or the voltage drop, and it's not a sudden drop like when you open a switch and the circuit's broken. It's a downward slide as the voltage starts to trend downward. But there's a unique phenomenon that you'll notice, that time will exponentially expand that it takes to get to the ceiling of the voltage or to absolute zero of the voltage. We'll see that in the lab simulator in a second here. Really quickly, any questions on that so far?
I think I'm good.
Okay, excellent. So, an analogy. I like the water terminology because we seem to use that early on in the term, and it's making sense for me. A capacitor is like a water tank for water that's already flowing through a system. And this is start to help you understand why we use capacitors. If we fill up the water tank and suddenly the water source shuts off, there's like a kink in the line or something happens, the water pouring out the other side continues to still go. Capacitors can help deal with inconsistent power sources because they store up the voltage, they store up the electrical charge, and they allow it to pass through the other side. So that gives us a practical application for a capacitor. They're great for, I think, Harley, you might have mentioned this, they're great for filtering, and we're going to talk about this more when we get into AC. They're great for filtering the line signal, filtering the flow of electricity. They're also great for inconsistent power sources or for systems that happen to be really susceptible to interference of some kind. The capacitors can help smooth that out because while they have some water in the tank, even if there's no more water coming in the system, they can still let some come out. They're also, as we talked about, really good at pushing out quick bursts, quick charges of electricity if they're needed, much faster than a power system, especially a DC system, can put out. Let me check time real quick, guys. It's 6:42, and our goal tonight is to not get Harley in trouble. Are we all in agreement on that one?
Agreed.
Okay, excellent.
I'll make it. Don't worry about me.
I constructed a small lab to show you how this would work, but it's also duplicated to some degree in the lab assignment. But since you guys are here, we're going to do it anyway. You guys get free points from me just for showing up. I want to talk about the application, and then we're going to jump into the lab together. Does that sound good?
Perfect.
Okay, cool.
Yes, sir.
All right, excellent. So applications where we can use capacitors. Let's be honest, everywhere. They are in the largest scale infrastructure, like Harley was talking about earlier, and on the smallest scale, electronics form factor, hobbyist, like personal computing, and the capacitors range in size from something larger than is feasible to even imagine as far as the farads that they contend with, and the micro capacitors. I use the field terminology, not micro like the system, the number system micro, but extremely small, like quarter uh, quarter millimeter like capacitors for small systems like tablets and phones and things like that. So systems that require bursts of power. Flash bulbs, rapidly flashing LEDs, sirens, flashlights, lighting, anything that needs to quickly have large bursts of power that a battery could not possibly contend with the need. Systems that require large amounts of power without ramp up. Ramp up is the time it takes for the voltage to slowly come up to the needs of the specification for where the circuit is. And you'll see some overlap with these two. So stator motors, torque steppers, halogen applications. These are all systems that need massive amounts of power, but they don't work well in the ramp up. They work well when they get to the voltage requirement. And also we use them for electrical quality control. And it's things like smoothing the voltage. If there's going to be a voltage drop and we can't have the voltage suddenly drop because it would cause like what's called an instantiated ground, where it looks like the ground voltage is something different than we intended it for. Or if there's voltage inconsistency where it's going up and down and up and down, and we need to smooth it into a very consistent voltage on the output, and for things like rectification. So that's something we're going to get more into when we start talking about AC in the next couple weeks. But these are the applications. So the best way I can describe an application for a capacitor is they are everywhere. I can't think of a good place where you would not have a capacitor in personal electronics, at least in this day and age. And that's really it for stop share for capacitors. Do the plates, are they losing or gaining electrons? The plates are gaining electrons and they're pushing electrons out of the other plate. No electrons are being generated, but they're essentially a capacitor is at max capacity when it meets the voltage of the battery. So it's trying to gain a state of equilibrium with the battery. And when that happens, then the electrons stop being pushed out. Do you want to take a look at that? Let me see if I can pull up a lab for you guys. Oh, Carlos has seen it. Excuse me, my twin has seen it. My twin's seen it all.
Don't forget, Carlos works with me too. He's seen all the same shit that I've seen.
That's
Excuse
right.
my language.
Carlos
Gotta throw him
has.
under the.
Oh, Carlos, you gonna put together a circuit for us? Import from text. Sorry, I'm trying to pull this up real quick for you guys. Okay, really quickly while I'm doing that, here is the virtual lab that I have for you guys this week. And I will give you a brief demonstration of what that's going to look like. Not the exact same one, but it's somewhat close. Actually, this is really close. Can you guys still see the screen or no?
Cannot.
Cannot, okay. Alright, I want to do that, and view that, and let's view the switch. Max scale, max scale, max scale. Alright, so what we're looking at here is a parallel circuit. That's, for some reason, got this really funky curve here. Anyway, a parallel circuit that has a voltage source of 5 volts. This is DC. We're still talking in DC. And here's our capacitor. And our capacitor is sitting in between the voltage source and the LED. And an LED is a light emitting diode, or a simple light, right? And the way this source is working is that when the switch is open, should the capacitor be charged, it will draw electricity off of the capacitor. And I use this demonstration, this schematic, because I want to show you exactly the rise and the fall of voltage within a circulation. My speed might be a little off, but I'm going to close this circuit. Yeah, that's a little fast. And I want to demonstrate, oh, that's real fast. And I want to demonstrate that what's happening, there we go. Let's do that. I'm going to reset this one more time. Actually, we're going to open the switch up. Can you see how the switch is open, but the LED is still on? The light is still going. What's happening here? There we go. That's good. Sorry, I'm looking at trying to create the scale that you can actually see this better. It works better in your lab than it does in my test guy here. So when we close the switch, the electrons are getting pushed into the capacitor. The capacitor is slowly charging up, and it ramps up very quickly, but in order to achieve its max voltage, it becomes exponentially slower. And that's typically the way that a small capacitance capacitor will work. It will ramp up very quickly to get within 80%, and then it'll start getting, well, 90%, and then it'll start slowly, exponentially slower, the voltage will start raising. So the point in actually reaching full voltage equilibrium with the power source is infinity. That's essentially how the scale ramps up, but it'll be up there. But when the circuit's open, it quickly drops. Can you guys see this scale? It's probably really hard to see. There it goes. Can you see how it's slowly scaling down? But initially, it drops very quickly. It's discharging as much electricity as the circuit will take almost. And then it slowly scales out. This right here is 0 volts, but it's exponentially ramping down. If I were to speed up the simulation, there we go. Can you see how it almost becomes a flat line, like a parallel line? Now I'm going to ramp up and charge the capacitor by closing the switch. And it almost instantly takes in and charges the capacitor far faster than any regular dielectric or chemical battery would be able to. And then it discharges. If there were a heavier load or something that required more energy in the system, this would happen almost instantaneously. It would be almost a vertical line down. And I want to kind of demonstrate the, whoops, we got a hot mic here. That's Harley. I'm going to mute you. Just raise your hand if you want me to unmute you, dude. I want to demonstrate, and that's the purpose for a capacitor. It's used for those applications where we have specific bursts of energy that are required within a system that a battery system cannot contend with, and then they're also good for smoothing out the drops or falls. I want you guys to pay attention to the LED. You see how it's almost instantly red? It's turning on because there's electrons flowing through it. As I open, let me turn the simulation speed back to normal. As I open the switch, the LED is still faintly glowing, and it's going to continue to decrease at a noticeable rate, which exponentially gets lower as the time scale goes on, but it's still allowing electricity to flow through the circuit even though there's no voltage source. Very much like a battery, but with some key differences. And those key differences, they don't create energy, right? They are able to be charged or able to be discharged, but they don't create energy. Far different than the chemical reactions that happen within batteries. Much lower storage potential than a battery of the same size or the same solution or the same dielectric makeup, but they're much faster at charging, much faster at discharging, whereas a battery is a much slower discharge. Does that make sense, guys? Sorry, I'm going to unmute Harley because I had to mute you because you had a hot mic. Okay. Oh yeah, you're playing around with Falstad, Carlos? Yeah, it's good. I actually really like. Um, it's got some quirks in there where you can't put a capacitor in there without a resistor, I believe. It's got to show some form of load, but it's an awesome application. Guys, I want to respect Harley's relationship. I don't want him to get in trouble. I don't want him in the doghouse. If anybody has any questions, please feel free to stay on. I will stay on for another couple minutes, and I would like to help as best I can start to get this down. I just didn't feel like it was really doing it justice in the text, and I wanna help you out with this. All right. Any questions on capacitors? Let me know. Other than that, I think we can turn off the recording.